Howdy, hackers, and welcome to another episode of FairLight TV. One of the news is that we broke 400,000 views. So, humble thanks, guys, for paying attention to what we're doing here. We are so grateful that we are able to entertain you. The other thing is that this episode is sort of consisting of two new elements. First of all, the core of what I'm telling today will be the same as we did in episode 4. But since it's now 3 years since that episode was done and it's sort of forgotten, we are reiterating it, brushing it up with content 2.0. So this is about compression, how you are going to achieve a lower sort of memory usage and disk usage of your files. But not only that, the part on sequence crunching, the LZ part, will be handled by a guest, and I'm not telling you who that is. You have to watch for yourself. So over to compression. So compression, what is it and what is it good for? Compression means that we take sort of a stream of data, a file, and then we pass it through an algorithm that is able to handle that stream of data so that it takes a smaller footprint on the disk. And then that smaller footprint file could be fed to a depacker, and then the data returns to its original size. Why do we do that? Well, I mean, back in the days when you had a 1541 disk drive for your Commodore 64, that disk is 170 kilobytes. So if you would like to utilize that as efficiently as possible, it was really, really key that you compressed stuff so they wouldn't sort of eat your very expensive disks. Basically the same is valid today, even if you have terabyte disk drives or terabyte hard disks. You have media files that are now so much bigger, so the ratio, the number of files you can store is not that, it hasn't changed that really much. So if you have video files, full length videos, it's of course so that you would like them shrunk to a size where you can have multiple on your media, rather than consuming all of that storage space with just a few files. So compression is still a thing today, even with modern hard disks and other kind of storage devices. The first distinction we should do is between the principle of lossy and lossless. Lossless is quite evident. You take the original, you run it through the algorithm, it sits on the disk in a very much smaller version of itself. You run it through the depacker or the de-inflation routine or whatever you like to call it, and then it returns to exactly the original. Lossy is not that. You take the original, the algorithm is making sort of small patches to the source data before it compresses it, so that it compresses a lot better. If you look at MP3, for instance, it makes small modification. If you take JPEG, it makes small modification. The footprint of the compressed instance is so much smaller than without those small patches. And then when you sort of inflate it back again, so you listen to your media or you watch your JPEG picture, the idea here is that the changes you have made should be so small that they are barely noticeable, and they are sort of justifiable for the gains, the small changes they are doing to the original file. So it's a trade balance between the efficiency of the compression, because if you want the compression to be really efficient, you need to make more significant changes to the file. but eventually you reach sort of a tipping point where you are introducing artifacts of the compression, and it's noticeable, and it's sort of disturbing. So if you're watching really hardly compressed video, for instance, you could see so many artifacts that it's really annoying to watch it. So that is the balance that you're sort of juggling with inside lossy compression. With lossless, not like that. It's always compressing to 100%. And really, lossless, it's sort of the only thing we did on the C64 and the Amiga. It's sort of only introduced for media files first, and then it's mainly done on sort of bigger systems. We didn't really have anything on the C64 that contained any kind of lossy compression. So let's have a bit of an example here. I took this from scantips.com. If you're using the higher compression grades on JPEG, you would see that you have a number of artifacts, blocky, vague dark smudges, and some false color changes. I'm not really sure I understand all of those words, but if you look at the example here, they are sort of pointing out a number of the places where you can see sort of changes taking place. Here, it looks very different from up here. You see this one is sort of the clear text, and if you look at this one, you would see artifacts outside. So these are changes introduced to the source material before compressing it so that it would compress more efficiently. Thanks to scantips.com for that picture, or those pictures. I'm going to go through 3 types of compression. It's run length encoding, RLE. The instances we see on the C64, they are predominantly called packers, but there were alternative names as well. Zipper was one by one particular person, or a number of names, but sort of the category name is packer. Huffman coding, not really a thing on the C64, so that is sort of introduced here only for reference. It has a bit of an application also for the next LZ or sequence crunchers, or we tended to call them crunchers on the C64. But I will also add a little bonus in the end. That's delta compression, and then and delta compression isn't actually compression. It's sort of recoding the original so that it would pack with RLE, and it's not changing anything. It's just representing the source data in a different way. And the really interesting part here is that I will actually have like a guest speaker. So for sequence crunching, we are going to rely on one of the real rock stars on the sequence crunching scene. So stay tuned for that. Okay, so you have your original file, the raw file that you want to handle. Depending on the type of file, you could apply sort of different strategies to it. If it's a runnable file, one of the normal way to handle it is that you pack it and then make it sort of self-extractable. That means that a little depacker is added to the beginning of the file before the pack data. So when you load that file, the depacker runs, it depacks the pack data so it becomes the original, and then start it. If you look at the C64 and also on the Amiga, when stuff like that was done, you typically saw some flickering of colors or a bit of a sound effect or something like that to show to you that the machine was actually working, because so you wouldn't get sort of annoyed that it didn't start even if you clicked it or started it. The other way to handle pack data would be stuff like level files. If you have a game that should load 1 or 2 or 3 files that consist of the level you're playing next, when you implement crunching into those scenarios, you take the depacker and then you have that inside the actual game. So you retrofit the game with the depacker. Typically that is also sort of combined with a fast loader. So a fast loader and depacker sits in the same package, and then that loads the level file that sits on the disk and transparently depack the data so that it lands in the memory in the shape of the original file. In those scenarios, of course, you don't need to append the depacker to every file because it sits once in the memory without being sort of repeated on every file. That's only relevant for running the files. In other scenarios, you could have packed data where you need a dedicated program to depack it. If you think of like zip on a bigger machine, that is packed data that sits there, but you need a dedicated program to depack it. It's not, there are self-extracting versions of zip as well, but normally it's just compression so that you reduce the footprint on the disk. And that is it. You need to have dedicated programs to kind of access the content of it. I mean, nowadays it's sort of built into the OS itself to depack it, but you need sort of dedicated code to actually access it. And of course, in the C64, we didn't have the depacker routines built into the ROM. That wouldn't fit at all. Run length encoding, that is the first compression mechanism that we are going to talk about. The idea here is that you minimize the footprint on disk by removing big chunks of repeated bytes with sort of a little sequence that tells the depacker the number of bytes and what byte that would be. I've seen this implemented basically in two ways. In commercial programs, I've seen sort of the option 1, and sort of the hacker instance of it is option 2, and we will go through both of them. So the depacker fetching the first byte in the packed data in sort of the picture format for Masquerade, which is one of those quirky adventure games that I've hacked my way through. And I've had special reason to kind of go through what the compression method was in this game, because I had broken pictures and I needed to have somebody help me repaint those pictures. So I had to depack and then find or code the compression mechanism to pack them back to the original format. So and I don't remember if sort of the bit 7 here I'm talking about should be 0 or 1 for representing each. That's not really relevant here. I'm just telling the basic principle. So bit 7 marks if it is a sequence, or it's marking a sequence of data that contains no repeated bytes. Let's call them literals, because inside sequence crunching, that's what they're called. And I know this is not sequence crunching, but that's still used out. So literals is a sequence of data that the depacker shouldn't handle. It should just kind of let them through, feed them to the depacked material, and that's the rest of it. So, but if the bit 7 here indicates that this is a number of bytes that are the same, then the next byte tells which byte it is. But that leaves bits 0 to 6, so the lowest 7 bits of that kind of parameter byte available, and that could be representing the length. So bit 7 represents literal, or that it's supposed to be a repeated byte, and then the lowest bits represent the length of that. For literals, of course, the number of bytes are just going to flow through the depacker, but if it's not, if it is marking that it's a repeated byte, the next byte tells that this is the byte to be repeated the time indicated by bit 0 to 6. I hope that was sort of understandable, even if it's not graphically shown rather than just explained here. What is more commonly used in sort of the hacked packers would be to fetch a control byte. So pass 1, you run through the program and you count the instance of each of the bytes inside the file. And you try to identify a byte that's never used or used as few times as possible. So you, out of the 256 options, you pick the byte that is represented the fewest time inside the file. That becomes a signal. So everything is a literal until you find that byte that is signaling that, okay, here comes a parameter. So the parameter byte then, when that is found, the next 2 bytes would be the length of this, of the packed, or the number of repetitions that the next byte should contain. So if you would find a parameter byte 65, then you would find 15 and 0. That would indicate that you would have 15 zeros. And then the depacker inflates that. So if you are sort of having real instances of the byte 65, my example of a control byte here, then you would have a string that would be something like 65, 1, 65. So depack this sequence into 1 byte of 65. So what should be like a literal byte of 1 becomes a byte of 3. So every instance of the control byte that where it's not used as a control byte but actually kind of appearing as a literal, you would make a loss of 2 bytes. But given the absolute gains in all the other scenarios where you find repeated bytes, that is a very small cost for inside sort of the packed data. A few things to remember by run length encoding. Everything is still handling bytes. We're not shifting anything into sort of over or across the boundaries of even 8-bit bytes. It's just handling bytes. And one of the other things that you might also know if you dive into packers on like the scene packers is that a number of them had multiple parameters. So it would count like 5 or 6 different control bytes, and then they would use those for specific things. It's really common that the empty areas of a game or a program would be zeros. So you could have a dedicated control byte for zeros. Then you would only need to send the parameter byte and then the number of bytes that you would like to see repeated. Because by finding that parameter byte, you would already know that it's zeros you wanted to depack based on that. But here you would have the sort of the logics of run length encoding packers. If you are adding more characters, the control byte of the last one you're adding is going to be repeatedly found in the destination find, very likely so. So you would need to, and that one would be represented at the loss in the if it's representing itself as a literal rather than being sort of a parameter. So adding more than a few, 3 or 4 or 5 special parameters where each of them will represent something that is a quirky thing that you are addressing, most of those wouldn't gain that much, and then you would have a loss in the output file due to the fact that they need to be represented sometimes. So if you look at files like the 6-code zippers, that one uses 6 codes, and I'm not really sure if it's all that efficient. If you look at the actual file, it might look like it's really good, but typically what you also did was applying a sequence cruncher on top of the run length encoding. And most of the time, the benefits from having a more sophisticated run length encoding was sort of lost after sequence crunching. Yeah, I hope that was clear, even if it was sort of fuzzy explained. Okay, Huffman, by a mathematician called Huffman. And let's first establish one of those terms used in this context, and that is entropy. So if data is evenly represented across sort of the entire space, so you have basically the equal numbers of zeros, 1 and 2, up until 256, and it's the same on all over them, and they are equally represented. That is the highest degree of entropy you can achieve. The lowest entropy would be if it's the same byte across the entire file. That's low entropy. And Huffman works better the lower the entropy. If you look at like normal binary file, the distribution across the bytes is typically rather well distributed. But if you look at special cases like text files, you would see that, first of all, almost all of the bytes are sort of the standard ASCII characters, the 0 to 128. And most of them wouldn't be under 32. And then you would also see that most of them are not capitals, they are small characters, and they are within a range of 64. And also those, you would see that the vowels are more represented than the consonants. So that is a typical case where you can throw Huffman in, and Huffman compression will do a rather good job. So what you do is not having bytes, but you are representing the commonly represented characters with a shorter code, like a 2 or 3 bits only. But of course, that also means that you need to have the least frequently represented ones represented via a longer code. So they could be represented by something much longer than the normal 8 bits of a character. And the idea that in a scenario of low entropy, the number of small sequences are so many that it outweighs the fact that you are making a loss on the less frequent characters. This is also sort of a thing that breaks the byte boundaries, because the source data is using sort of 8 bits, so bytes, whereas the destination data would be a few bits. And then of course you need to have the output data stored across byte boundaries, otherwise it wouldn't make any sense. This is rarely a thing for the C64. There are a number of implementations of it, and yeah, it could do good jobs on certain files. But if you look at sort of packing runnable code, it would never do anything fairly standard, or it wouldn't be competitive compared to the sequence crunchers that we would eventually go into in the next phase of this one. I'm showing here the link to Huffman coding. That's the Wikipedia article on Huffman coding. But I can also say that I've taken those 2 pictures. So this is sort of showing to you that using one of those Huffman trees, you are establishing the frequency of the characters, and you are allocating the characters that are frequently used a short code, and then eventually by the end of the table you are seeing here that the least represented characters get a longer code, and this is only using one little sentence here. But if you have all the characters, and then you would have the last characters, the least frequently used characters, that would have a much longer code than this, because as it's represented here, it's actually making a win on all characters, but that's not true in real life. Right. All right, and then LZ. That's a technology named by Lempel-Ziv, or named after the 2 founders, Lempel and Ziv. These are the family names of the 2 guys that did this. This one is not working with repetition of bytes, it's finding repeated data. So if the same data is repeated multiple times inside the file, rather than repeating the data, you are placing a reference to the other data and also the length. So you would have a pointer and length pair, or a distance and length, I think it's called actually in the description of this. And then the size of the pointer is depending on the window that you would like to look into. So the bigger window, the longer crunching times, because then you would need to look into the occurrence of that little sequence you're finding in all of that window. And then since you are packing, it's also called sliding window, because that's that sort of reference window. Size is one thing, but also where it is in memory depends on when you depack. So when you are depacking, that window is sliding as well. So the offset is not sort of absolute. It's relative to where you are inside that window. And the bigger sliding window means that it takes longer time to crunch, and you would also need a longer offset. That reference needs to be longer. You need to have more bits to be able to point to a bigger window. So it's not, you are likely to find additional sequences in that window if you are increasing the window. But on the other hand, since the reference is growing, all the cases where you find your windows would also increase in size. So you are sort of gaining less with each of the references you are making. But since you possibly find more, you could win it back, but it's not sure. Also here, the output breaks byte boundaries. So when you look at the data that you have been packing using LZ, it looks like garbage. There is nothing you can find there that makes any sort of sense. It's just random bit noise. But in order to find a better explanation of this, I have actually invited one of the ultimate experts on the topic. I've invited Øyvind Åsheim, whom you know as Matcham of Network. He's the guy that produced the Time Cruncher. That's sort of the first instance of LZ compression on the C64 that used variable sizes of the 2 byte pairs here, or the byte pair, the 2 bytes, the byte pair. It's not 2 bytes then, because it's variable length. But I will leave you to listen to Matcham explaining this in a much better detail than I ever could. So over to Matcham.
Hello everyone, my name is Øyvind Åsheim. In 1987, I, under the handle Matcham, created compression tools for the Commodore 64 home computer. And Time Cruncher is a dictionary-less equal sequences compressor. It's a Lempel-Ziv variant. It finds duplicate sequences within a sliding history window and refers to them as matches. And the compressed output alternates between literal elements and match elements. A literal element is a pair consisting of the length of the literal data and the data itself. A match element is a pair that references a match in the history window using its length and distance. And the length, distance, and literal count values are integers encoded using a variable number of bits. And the sequences as short as 2 bytes can be compressed due to the very compact encoding system. I think of that as the main novelty of the Time Cruncher algorithm. Alright, let's dive into a compression example using a simple buffer, hover bover, and jumpman. This buffer has 3 duplicate sequences, as we can see in colors here, ov, var, underscore, and an. And here's how we compress it. We move a pointer through the buffer. At the pointer's position, we have a look-ahead window, and behind it a history window. As the pointer moves, we look for the longest sequence in the history window that matches the start of the look-ahead window. If we find a long enough match, we replace it with a match element which uses fewer bits. If no match is found, we add the byte at the pointer to literal data. Let's see this in action. After 7 bytes, we find our first match, and we prepare by adding literal element of 7 bytes to the compressed buffer. The match is OV, has a length 2, and is located 4 bytes into the history window. As we can see, we add a corresponding match element to compressed buffer. And we immediately see a new match with the var underscore. Before adding it, we add a 0 byte literal element to compressed buffer. Now the match sequence is 4 bytes long and is found 3 bytes back, so we add that as a corresponding match element. And now there are no new matches until the second n. So we add 9 bytes of literal element to compressed buffer. The distance to the previous n is 7, so we add a match element with that distance. And finally we add a 1 byte literal element to include the period character to compressed buffer. So we have completed the compression, and it looks like this. And here's how to decompress it. We start by reading the first literal element and outputs the literals to decompressed buffer. Next we process a match element of length 2 and distance 4. This means we look 4 bytes back in the output to find the sequence OV, which we append to the output. We then process an empty literal element which doesn't change our output. Moving on, we process a match element of length 4 and distance 3 to find the sequence var underscore. We next read literal element of length 9 and output the literals. Then we find a next sequence of length 2 and distance 7, which gives us an, which we add to the output. Finally, we process the last literal element, which is 1 byte, and output it. And that's it. Our decompression is complete. We have our original string back. Okay, let's talk about how we encode the numbers using variable length encoding. So, imagine we're storing numbers in a bit stream. The first thing we do is use 1 or more bit flags to specify the value range. After that, we use a specific number of bits to store the actual value within that range. Now, for instance, storing the numbers 2 or 3 can be done with just 2 bits. We use 0 as the bit flag, and then as the bit 0 for the value 2, or bit 1 for the value 3. It's simple, right? Now, for lengths between 4 and 7, we use the bit flags 1, 0, followed by 2 bits for the value. For lengths between 8 and 23, we use 1, 1, 0 plus 4 bits. And for lengths between 24 and 279, we use 1, 1, 1 plus 8 more bits for the value. The actual variable length encoding layouts are in the original code, but I don't remember them exactly. So they're shown here just for illustration purposes, and they changed quite a bit from version 3 to version 4 of the time cruncher. So what you'll see here won't be exactly what's in the original code. Alright, let's talk about how we encode the distance and the literal count using variable length encoding. These values have different distributions, and we use different encoding layouts to save space. The process is similar to what we did for the length variable. And we start with 1 or more bit flags, Then we use a designated number of bits to store the actual value. So for distance, here's how it might work. For values between 0 and 63, we use 0 as the bit flag and 6 bits for the value. Between 64 and 1079, we use 10 as the bit flags and then 10 bits for the value. Between 1080 and above, we use 11 as the bit flags and 13 value bits. For literal count, it's a bit different. For values between 0 and 3, we use 0 as the bit flag and 2 value bits. Between 4 and 11, 10 as the bit flags and 3 value bits. Between 12 and 522, we use 11 as the bit flags and 9 value bits. For some very even frequent higher values, we use 11 ones as the bit flags and then additional 16 value bits. Alright, let's see how much space we saved. So this is our compressed buffer. And the first sequence is 2 bytes or 16 bits. It was compressed as this. To encode these 3 values, we used 14 bits, as can be seen here. Thus, we saved 2 bits on the first string. On the second string, or 4 bytes or 32 bits, we compressed it as literal count 0, length 4 and distance 3. The encoding of this also totals 14 bits. So here we saved a whopping 18 bits. The final sequence is again 2 bytes. We compressed it as this using 14 bits, so we saved 2 more bits. We also encoded the final literal count with 3 bits. So in total we saved 2 plus 18 plus 2 minus 3, which equals 19 bits, and this rounds down to 2 bytes. So we didn't save that much on this short string. But remember, compression usually gets better with a longer input. And I hope you enjoyed this short presentation of the Time Cruncher from 1987. I also would like to mention that today I'm busy by developing a travel search engine called FairLight. And here you can find flights in combination with trains or buses. And that's a good way to compress prices and also emissions. It has price calendars, explore maps, it even has a traveling salesman optimized multi-city routing engine included. So feel free to check out FairLight. Thank you and bye bye.
Thanks, Øyvind. That was absolutely great. And we did notice you managed to squeeze in a bit of a marketing for your current employer there. All good, all good. I wish you the best with that as well. And thank you so much for your effort. And if you liked Øyvind's talk here, next week we will actually have an interview with Øyvind and have a broader talk about his implementation of this and the history around it. And I know Øyvind was sort of active in the scene before most of you bought your C64, and he actually sold his C64 going Amiga also before many of you started. But he's one of the original rock stars of the C64 scene, so that is a name you should know if you kind of have the opinion of yourself that you are scene aware. I've made a little list of sort of the history of the implementations of LZ, or LZ77 if we should be specific here, on the C64. So Time Cruncher was sort of the first one that also included this variable offset distance pair. You would have other compressors that also sort of implemented LZ, but they were less efficient. There was it super compressor, but also the 1001 Cruise Card Cruncher was also implementing this. But when Time Cruncher came about, that was the cruncher that sort of obliterated the competition. That was the first step into a new territory. It broke new ground. Galleon of Sphinx took Time Cruncher, reassembled it, and tried to optimize it, making it faster, making it more efficient, thereby possibly even making it slower. And his version of Time Crunch became sort of in a league of its own, Cruel Crunch. That took over sort of the reign of Time Cruncher, and it became the most efficient one, but it took forever. Christopher Cassel, so Galleon, had the best cruncher for a number of years. I think he started when he was in Sphinx, and then I was actually there starting One Way with him, even if I was only in One Way for a week before I left for FairLight. So I do know Christopher a bit, but let's see if we can have a little talk with him as well. The next one, it's not actually better in compression, but it took sort of a quantum leap in usability. Dark Squeezer by Dark Force of the Sharks. It said that his first one was also heavily based on Time Crunch, but eventually it grew a lot better than the original Cruel Crunch, the original Time Crunch. But he also added support for RAM expansion unit. And that made a lot of difference when it comes to crunching time. So even if the crunching efficiency wasn't, that much better, it took a fraction of the original time. We were talking minutes rather than hours, and that takes, and that is worth a lot. So even if it didn't sort of beat Cruel Crunch on crunching efficiency, it most of the time were at par with Cruel Crunch. And if it could be at par or one block worse, and I would spend a few minutes rather than 8 hours, I'm sorry, I took that potential risk of being one block longer because of using Dark Squeezer. So Dark Squeezer was my go-to tool for a number of years. The IFFL we did, my level crunching and the normal crunching, all of that used Dark Squeezer because it was so good and so convenient. The next step was Sisyphus and Skyflash, Fredrik Hederstjärna och Dav Hovang. They implemented the Cruncher AB or the AB Cruncher. It was expressed both ways. If you look at CSDB, you will find sort of names, both AB Cruncher and the Cruncher AB. And then also Byte Boiler. And to be honest, I'm not really sure which is the better of those. And they implemented something that was LZHH. So it's LZ from the original authors, Lempel-Ziv, and then Hederstjärna and Hovang, their respective family names. So that was also something that I was using a lot. And they also implemented support for RAM expansion unit, I should say. So they were also providing excellent results. And on top of that, also really, really fast. I don't think I ever used them for level crunching. I only used it for crunching runnable files. I wonder why I didn't do that for level crunching. That should also be quite fine. All right, nowadays I am using Exomizer, and Exomizer is Magnus Lind, I think. Sargon of Light was his original handle when he was doing his scene stuff. So that is a program that does the compression on a bigger machine, and I'm running it now under, I don't know, 3 gigahertz or whatever my machine is doing with multiple cores and all of that, and it still takes, 20 seconds to compress a real file. So imagine what that would take on the C64. It would take forever. but it's also doing a really massively good work. It's doing better job than any of the others I've listed here. Okay, so that was a bit of a history lesson on the implementation of LZ on the C64. Okay, so this is not the technology on its own. It's just sort of a trick that you can apply if you would have something which is sort of an animation, and if you want to store that in memory rather efficiently. Delta packing, it's not actually packing, but you take a reference frame and then you apply an XOR with the same byte on the current frame. So let's say you have frame 0 and you are now on frame 5. You take the first byte of your frame 5 and then you compare it with the original reference frame, the frame 0. If they are the same, the XOR would result in 0. So you take the original byte, you take the other byte, XOR them, and XOR would sort of zero out if they are the same. And then you take the entire frame like that, and then your frame would not be represented by the actual bitmap data. It would be represented by the difference between that frame and the original frame. And if you apply run length encoding on that, all the areas that are the same would be zeros, and they would compress really efficiently with run length encoding. So the additional frame could be fantastically small if not much change from the original one. That is the trick for doing animations without wasting that much data. It's a rather neat trick. So that was a little bonus thing I threw in there. That was everything we managed to squeeze into this episode about compression. Thank you so much for being one who added to our 400,000 view. Let's go for 500,000 in the near future. If you like this, feel free to subscribe. Please do that. Feel free to share it with friends, because every week there is somebody who complains that they didn't find the show. Even if it's been around for over 3 years now. And also feel free to visit Redbubble, search for FairLight, and there you will find our nice t-shirt, including one with the logo I have behind me here. See you next time. And I can already tell you that next time will be with Øyvind Matcham. That would be something to look forward to. See you then. Bye-bye.
This station is now the ultimate power in the universe.
FairLight.